Good afternoon, everyone. It's very grateful to have this opportunity to attend this ASHRAE seminar. My name is Zhang Shen. I'm a PhD candidate in the Building Energy and Environmental System Laboratory at Syracuse University. Today, I will present something about ozone emission sources and the surface removal in indoor environments. By attending this seminar, you are supposed to learn something about these four topics. And I will present from the background of ozone and the introduction of indoor ozone, and then introduce the indoor ozone estimation, indoor ozone emission source, and the surface removal by building materials. At the end, a tool for estimating indoor ozone concentration will be introduced. Ozone is a very reactive gas that can react readily with many other chemicals. It can also impact people's health. For example, it can have negative health effects on lung functions, increase respiratory related disease, and even result in premature mortality. Generally speaking, outdoor ozone concentration is usually higher than indoor concentration. However, considering that people spend almost 90% of their time indoors, the indoor exposure may be considerable. According to a review, indoor ozone exposure accounts for around 60% of daily ozone exposure. When considering the breathing rates in indoor and outdoor environments, indoor ozone intake accounts for around 40% of daily ozone intake. This is still a very high proportion. So therefore, indoor ozone is very important for people's health. The indoor-outdoor ratio represents the relationship between indoor and outdoor ozone concentrations. A literature review indicates that the IO ratio of ozone in different buildings at different locations is generally within the range of zero point 0.2 to zero point 0.7. The right side here shows a diagram of indoor and outdoor ozone concentration we measured in a student dormitory. The IO ratio is around zero point 0.2 to zero point 0.4. It's generally within the typical range in here. Like many other indoor pollutants, indoor concentration of ozone also depends on the source and the removal. The major source of indoor ozone is the outdoor ozone entering buildings through nature or mechanical ventilation or infiltration through cracks. Some indoor devices like laser printers, photocopiers, and some air cleaners can also generate ozone. Regarding the removal of indoor ozone, um, indoor ozone can be removed through air changes and also through reactions between ozone and other compounds, like other gas chemicals, and also indoor material surfaces like floor, walls, and furniture, and also reaction with human surfaces like human skin. The ozone concentration in indoor environments can be estimated by this single zone mass balance model. Um, in this presentation, I will just focus on the indoor ozone source from indoor ozone emission devices and the surface removal by building materials. Some devices used in household and office settings can generate ozone during their operations. For example, some disinfectors that use ozone for disinfection, and some air cleaners, and also printing devices like laser printers and photocopiers. According to a survey we conducted before in China, many people actually will use some of these devices in their homes. And the table here shows some common indoor ozone emission devices used in indoor settings. These devices can generate ozone mainly through two different ways. One is through corona discharge, and another way is through photochemistry. In the absence of protective measures like activated carbon filters, some of these devices can generate ozone and then introduce ozone to the room air. Some ozone emission devices intentionally generate ozone and use ozone for disinfection. They are also known as ozone generators, while others did not intentionally generate ozone, while they produce ozone as a byproduct during their operations. But the ozone emission from both of them actually require certain attention when people are using them. Ozone emission devices can generate ozone mainly through these two different mechanisms. The corona discharge is widely used in printing devices and some air cleaners. For air cleaners, they usually use corona discharge for capturing particles. Another ozone generation mechanism is photochemistry. The UV irradiation between 200 nanometer and 300 nanometer can inactivate microorganisms. Therefore, uh, this UV irradiation is widely used for air disinfection. So, a low pressure mercury lamp can generate UV irradiation at 254 nanometer, which can be used for disinfection. And actually, it will not generate ozone at um, this wavelength. But this kind of low pressure mercury lamp can also produce UV light at 185 nanometer. And this UV light is actually within the vacuum UV range. And the vacuum UV range can generate ozone by oxygen decomposition and recombination through the process in here. Therefore, some UV disinfectors and devices that use UV lamps may generate ozone during their operations. This diagram here shows the ozone emission rates of different indoor ozone emission devices from the literature data. The devices are classified into six types, including induct air cleaners, ozone generators, room air purifiers, photocopiers, laser printers, and other devices. The box plot below shows the distribution of ozone emission rates for different devices. Generally speaking, ozone generator and induct air cleaner have the highest ozone emission rate with an average of 76.3 milligram per hour and 62.8 milligram per hour. And the room air cleaners and the photocopiers have comparable ozone emission rates and are much lower than the ozone generators and induct air cleaners, with an average at around 3 or 4 milligram per hour. And the laser printer and other small devices have lowest emission rates. For laser printer and photocopiers, the average ozone emission rates uh, per paper is also calculated. The unit emission rate per paper for photocopier is much higher than a laser printer. The average ozone emission rate per kilowatt hour for the other devices are also calculated. The unit ozone emission rate per kilowatt hour for room air cleaners is lowest among these devices, and it's around zero point 0.3 gram per kilowatt hour. Except ozone, these ozone emission devices can also generate other byproducts like VOCs and particles. And printers and photocopiers can also generate considerable heat during their operations. Okay, here let's move to the ozone removal by building surfaces. Building materials can be significant things for indoor ozone due to the reactions between ozone and the materials. The reaction may also result in oxidized byproducts yields, which can also impact people's health. When ozone reacts with unsaturated organic compounds, it will usually generate significant byproducts, and ozone can be removed a lot. When ozone reacts with inorganic materials, usually negligible byproducts will be generated. The ozone removal at the building surfaces generally depends on the transport of ozone from room air to the area near material surfaces, and also and then the uptake of ozone onto the surfaces. The rate of ozone removal can be quantified by deposition velocity, VD. It can be calculated by the equation here. It depending on the transport limited deposition velocity, VT, and the reaction limited deposition velocity, VS. VT, transport limited deposition velocity, depends on the boundary layer fluid mechanics near material surfaces. VS, reaction limited deposition velocity, depends on material characteristics. Therefore, it is material specific and system independent. It can be quantified by reaction probability. Reaction probability of material represents the ratio of removal rate to the creation rate of ozone on the surface. This diagram shows the impact of material reaction probability and fluid mechanics on ozone deposition velocity. The dashed line represents different transport limited deposition velocities, and when reaction probability is lower than 5 times 10 to minus 7, reaction deposition velocity is only dependent on reaction probabilities. Therefore, deposition is reaction limited. When reaction probability is larger than 3 times 10 to minus 4, reaction probability does not impact the deposition, and the deposition is only impacted by the transport. So therefore, the deposition within this range is transport limited. And the dots in the diagram represent the experimental results of deposition and the reaction probability of different materials from the data in literature. It can be observed that most materials are located in the middle part in here, which indicates that the deposition velocity of most materials are dependent on both reaction and transport. Therefore, both fluid mechanics near material surface and the material characteristics are important for determining ozone removal by building materials. The diagram here shows the reaction probability of different materials from the data in previous studies. The material on the left side have lower reaction probabilities, like glass and metal, and the material on the right side have highest reaction probabilities, including activated carbon and bricks. The table on the right side of the page lists the median value of reaction probability for each material. From the result in here, we can observe that the reaction probabilities of building materials depends on material chemical compounds and also surface characteristics like roughness and porosity. For material chemical compounds, unsaturated organic compounds are highly reactive with ozone and may produce considerable oxidized byproducts. In addition, materials containing clays like bricks, gypsum boards, clay-based paintings, and ceiling tiles can consume ozone significantly while produce negligible byproducts. It's probably due to the reaction catalyzed by metals in the clay. And for surface characteristics, frizzy and porous material have higher reaction probabilities than smooth and non-porous surfaces. And also, specific surface area of material is more related to ozone reaction probability than total pore volume. And some materials may have surface treatments like paintings or coverings, and then the surface layer actually are more important than the underlying materials in determining ozone deposition. Ozone deposition also depends on transport limited deposition velocity. The VT measured in field tests and in laboratory experiments are actually consistent with each other. Both are between zero point 0.1 and almost zero point 0.7 or zero point 0.8 centimeter per second. And the value of VT can actually vary greatly even in the same room and can be influenced by air movement near the surface. According to the research data, the VT on the cabinet and the desk is very small, generally below zero point 0.1 centimeter per second. And the VT near hood and the computer is around 0.12 to 0.14. And the VT near window and the supply vent, while air movement is stronger, can reach 0.52 centimeter per second. The reaction between ozone and the materials may result in the formation of oxidized byproducts, mainly due to the reaction between ozone and unsaturated organic compounds. Some studies did measurements for carpet and observed that high byproducts use dominated by C9 aldehyde. And also, human skin oil is also highly reactive with ozone. Um, but generally, inorganic materials usually have negligible byproducts formation. Um, some inorganic materials like bricks, clay-based plaster, and protein-based tiles are usually considered as passive removal materials for indoor air, which can be used to reduce indoor ozone concentrations because these materials can remove substantial ozone while generate negligible byproducts. Okay. Over a relatively short period of ozone exposure, materials may become less reactive, likely due to the consumption of reaction sites on material surfaces. However, over longer term exposure to ozone, some materials may remain high surface reactivity due to the replenishment of reaction compounds on material surfaces, which is associated with occupants and their activities. Material surfaces may be soiled by skin oil, and activities like cleaning and cooking can also increase the reactive sites on surfaces. Ozone concentration can be easily estimated through the single zone mass balance model. if we know all the parameters in the equation. So based on the data of reaction probability of typical indoor materials, which we already introduced in this presentation, and also the database of ozone emission rates of typical indoor ozone emission devices, we also introduced in here. Um, then we can easily calculate the indoor ozone concentration. Well, of course, we need to know the ventilation rate and also outdoor ozone concentration and the room dimensions as well. So we developed this um, estimation model, estimation tool for indoor ozone concentration. It can calculate both steady state and dynamic modeling for indoor ozone concentration. And this tool was validated by the field data measured in a college dormitory. And okay, in this presentation, the ozone emission rates of a typical indoor ozone emission devices were introduced, and also the uh, surface removal by building materials is also introduced, and the reaction probability of different materials were introduced as well. And the reaction probability depends on material, chemical compounds, and surface characteristics. And the reaction between ozone and unsaturated organic compounds can generate considerable oxidized byproducts, while inorganic materials usually generate little. Materials may become less reactive after a short period of exposure to ozone. However, after longer exposure, the occupants and their activities may increase the reactive sites on material surfaces. Therefore, the materials may remain a very high reaction probability. Here are some references related to this presentation. And that's it for my presentation. Thanks for your attention. If you have any question, please feel free to contact me through this email. Thank you very much.